Hello everyone, thanks for joining this talk. I'm Rankyung from University of Minnesota, and this work has been done with my advisor Abhishek Chandra. Today we are going to talk about a new generic decentralized distributed deep learning system in microclouds. We will discuss about first, why we need to study about deep learning in microcloud. Second, what are the challenges of learning in such environments? Third, how the system DLion addresses the challenges in order to reduce training time and increase model accuracy. Lastly, we will see evaluation result. All right, then let's get started. Deep learning is a popular technique to build models from a large volume of data. The data is continuously generated from the edges across the globe, such as home IoT devices, smartphones, or surveillance cameras. And the data may contain personal information. To utilize such data for deep learning training, one simple way we can do is move all the data into the centralized public clouds. However, migrating such large amount of data over WANs for training is likely to be prohibited due to cost, performance, or privacy reasons. So, an attractive way is to carry out distributed deep learning across microclouds, which is an emerging type of infrastructure like small-scale clouds deployed near edge devices in multiple locations to support the exponentially growing large volume of data from the edge. The microclouds often provide better computation, storage, and energy capability than edges, and better data locality than public clouds. There are two major system challenges in enabling distributed deep learning in microclouds. First, computation resources can be heterogeneous. The number of machines and the types of computational hardware are not identical among machines and also among microclouds. Second, network bandwidth can be heterogeneous since the machines are connected over LANs and WANs. In addition, these available system resources may dynamically change over the time. There are two distributed deep learning architectures. First, and traditional architecture is a centralized distributed deep learning system, where a decentralized module called parameter servers to maintain a shared single deep learning model for workers. It's an efficient architecture to do one-time deep learning over fixed training data at a single location. To apply this architecture to the microcloud-based learning, you need to move all the training data to the centralized public clouds. However, it has limitations as we discussed in the previous slide. Otherwise, you need to solve the placement problem for the centralized module parameter servers. System performance is extremely varying based on the number of parameter servers and where to place them. So the other architecture is decentralized distributed deep learning. Since we have new considerations, such as data movement is restricted for cost, performance, and privacy reasons, and the data are geo-distributed and continuously evolving at many locations. For such learning in microcloud, this decentralized system without using centralized module has better fit for this case. Workers are the only entity for the deep learning training, and they exchange gradient with each other and maintain their own local deep learning model. Therefore, we propose a system DLion, which is a decentralized distributed deep learning in microcloud. There are three system design goals. First, maximizing data parallelism by handling different computation capacities of workers. Second, reducing communication costs by handling available network bandwidth among workers. Third, improving model accuracy by sharing knowledge with workers. These goals are to achieve faster training time and higher model accuracy. DLion has three major techniques for its design goal, and these techniques are applied to different training steps. You can see a workflow of each worker performing for an iteration. First technique, weighted dynamic batching, is applied to maximize data parallelism when workers compute gradients. Second technique, per link prioritized gradient exchange, is applied to reduce communication costs before they exchange gradient with other workers. Third technique, direct knowledge transfer, is a periodic update of local model with best weights to improve model accuracy. Let me elaborate the techniques one by one. The first technique, weighted dynamic batching, is to maximizing data parallelism to make the model convergence faster. Existing research has shown that increasing global batch size can shorten training time, where the global batch size is the total batch size used for a single iteration. However, it may decrease model accuracy if too huge batch is used for training. So, DLion automatically and dynamically increases the global batch size during training with a little cost of accuracy. Given the global batch size, DLion assigns a local batch size for individual workers based on their available computation capacities. Larger batches are assigned to higher performing workers, and smaller batches are assigned to lower performing workers. They compute gradients over the different size of training data. Even though the size of calculated gradients are the same, the size of training data differ from each other. So we come up with a confidence coefficient to give different weights for received gradient when updating the local model. This technique is mainly for improving training time with a minimal cost of accuracy. The second technique is per link prioritized gradient exchange. This is to select partial gradients with consideration of available network bandwidth before workers exchange their gradient with each other. But here we should think about trade-off. If workers use too small partial gradients due to scarce network resources, the model accuracy can be deteriorated. On the other hand, if they use too large partial gradients, it may lead to slow transmission time. Therefore, DLion finds a sweet spot to assure both fast transmission speed and high data quality with consideration of the available network resources. This technique is also mainly for shortening training time with a little cost of model accuracy. The last technique, direct knowledge transfer, is used to compensate for any adverse impact on accuracy by the two previous techniques. In the typical decentralized deep learning systems like Echo, Gaia, Hope, and Prague, the workers update their local model by exchanging gradients every iteration. In DLion, the workers periodically synchronize their local model with best weight sharing along with the gradients. We have explored when to send, whom to send, and how to merge weights. You can find the details in the paper. Weight exchange is proceeded not every iteration, but like every 100 iteration or every epoch. So the impact on consuming network bandwidth is negligible. Besides, the technique has positive impact on faster model convergence, so it ends up shortened training time as well as higher model accuracy. Now let's move on evaluation result. We have a prototype of DLion on TensorFlow. We use two image recognition applications using Cipher and MobileNet models with CIFA10 and ImageNet dataset. The applications are trained on either local CPU cluster or Amazon GPU cluster. We evaluate DLion with these four systems. Baseline is to exchange whole gradients with every workers. Echo and Gaia are exchanging partial gradients with every workers. They have their own algorithm to select partial gradients. And Hope is to share whole gradients with a subset of workers by excluding stragglers. These are emulated microcloud environments we use for evaluations. Homo indicate homogeneous resources, hetero indicate heterogeneous resources. CPU and net indicate only computation or network resources are varying respectively. Cis indicates both resources are emulated. And dynamic means the resources change while running experiments. These two graphs show that DLion outperforms other systems for every cases. Left graph shows DLion has the highest model accuracy when a Cipher model is trained for 1500 seconds on CPU cluster. And the right graph shows our system again has the highest model accuracy when MobileNet is trained for 2 hours on GPU cluster. Perlink prioritizes gradient exchange and direct knowledge transfer techniques play a key role for fast training time with higher model accuracy. This graph shows the ultimate model accuracy and required training time when the Cipher model is fully converged. DLion gets the highest model accuracy, although it requires a bit longer training time than Gaia and Echo. Because DLion assures data quality as well as transmission speed when exchanging gradients. The huge accuracy improvement was enabled by periodic synchronization of deep learning model with best weights. This slide shows that DLion has a capability to handle resource dynamism. The left graph shows different batch size assigned to each worker based on the changing available computation resources by DLion's first technique, weighted dynamic batching. The right graph shows DLion's another technique, Perlink prioritized gradient exchange, adjust gradient size based on the dynamically changing network bandwidth. DLion outperforms other systems in dynamic heterogeneous environments as shown in this graph. In conclusion, today we propose a decentralized distributed deep learning system, DLion, in order to converge deep learning models faster with higher model accuracy in microclouds by utilizing three introduced techniques. We see this system improved 4.2 times speed up in GPU cluster and 2 times trained faster and 26% higher accuracy it achieved in CPU cluster. This is all for today's talk. Thanks for listening. Any questions are welcome.